All right, folks. Chapter 13, Section 2, Day 1, Derivatives of Vector Functions. All right, we have already looked at calculating limits of vector-valued functions. Today we're going to look at how to find derivatives, which should make sense, right? We remember that a derivative is based on a limit of our difference quotients. So the derivative of r prime of a vector-valued function r is defined in much the same way as for real-valued functions. So dr dt can be represented as r prime of t, which is the limit as h goes to 0 of r of t plus h minus r of t over h. It's the same definition we saw last year. We have to be a little careful because what these things represent now are more towards vector things, but otherwise the ideas are going to be similar here. So if you see our geometric significance pictures right here, if we have points P and Q, with their position vectors r of t and r of t plus h. So those are those green lines right there. Remember, those position vectors just point at the points from the origin. Then the vector pq represents the vector r of t plus h minus r of t, which we can think about as the secant vector. So instead of talking about a secant line like we did last year, we're talking about a vector. In the diagram on the right, if h is greater than 0, then our difference quotient has the same direction as that secant vector. Excuse me. And as h goes to 0, it appears that this vector approaches a vector that lies on the tangent line, namely r prime of t. So very similar to last year, but our secant vector as h goes to 0 will approach our tangent vector. So r prime of t is called the tangent vector to the curve defined by r at the point P, provided r prime of t exists and is not the 0 vector. It points in the direction of increasing parameter. So we don't just have a tangent line that we can think about. We have to think about a tangent vector, and there is a direction associated with it. So if our curve, so I'm up here on the picture on the right, is traveling in an increasing t direction in the way that I'm drawing, which kind of looks leftish to rightish, then r prime of t, that vector, that tangent vector, is going to point in the direction of the increasing parameter. The tangent line to C at the point P is defined as the line through P that is parallel to our tangent vector r prime. So if we want to think about it like a line, we can, but most of the time we're just going to be using the vector. So our first theorem right here states that if we have our vector function r of t defined as the components f, g, and h of t, where f, g, and h are differentiable functions, then the derivative of r is just the vector that is made up of the derivatives of the component functions, f prime, g prime, and h prime. A unit vector that has the same direction as the tangent vector is called the unit tangent vector t and is defined as the derivative vector r prime over its magnitude. That should make sense. That's how we get a unit vector always. And this thing right here is going to be super useful all year long. Commit this to memory. How do we get the unit tangent vector, which we're going to call capital T? Notice it's bolded, so if you were writing it, you would put an arrow above it. How do you get that unit tangent vector? You're going to take a vector function, find its derivative, find its magnitude, and then divide that derivative vector by the magnitude. The second derivative of a function r is the derivative of r prime, namely r double prime. Similar to real valued functions, higher ordered derivatives are defined in the same way. So, the beginnings of this should feel pretty straightforward, I can imagine, as long as you remember how to take derivatives. So we're going to find the derivative of r of t, which is 1 over ti plus e to the 2tj minus 2 cosine of pi tk. Our functions, f of t g of t and h of t are right here, and all we're going to do is find the derivative of each of those. So f prime of t is the derivative of 1 over t, which is negative 1 over t squared. I'm hoping I don't need to, but I guess I'll write it down. You can think about that as t to the negative 1 and use power rule. G prime of t, the derivative of e to the 2t. We need a little bit of chain rule right here. Don't forget that. That's e to the 2e to the 2t. And then finally, for h of t, we need a little bit of chain rule here. We're going to take the derivative of cosine, which is negative sine, which will give us 2 sine of pi t times pi, which very rarely, I don't know why I just wrote a 3, very rarely will I be explaining chain rule like that anymore. That's going to just be 2 pi sine of pi t, so our derivative of our vector function r is going to be the components negative 1 over t squared, comma 2e to the 2t, comma 2 pi sine of pi t, which we can write with ij and k, but I am not going to do that at this time. You can, though. All right, we're going to find the unit tangent vector at the point where t equals 1. Now, finding the unit tangent vector, it is challenging to do for a general vector, leaving it in terms of t. The algebra is going to get a little messy whenever we have to do that. But when we are being asked to find it at a point where t equals 1, we can get around the gnarly algebra of it all and use some values of things. So, first of all, the unit tangent vector, not at t, at 1, is r prime of 1 over the magnitude of r prime of 1. So instead of needing to find the magnitude of r prime, imagine finding the magnitude of this, taking all of those components, squaring them under a square root, and taking those 3 components and dividing it by that thing, and then plugging in 1. Sounds like a nightmare to me. So it might make sense for us to take r prime, plug in 1 instead, and use this. So that is going to be negative 1 over 1 squared, comma 2e to the 2 times 1, comma 2 pi sine of 1 pi, which that's going to become negative 1, 2e squared, and 0. From this, we can find the magnitude, and I'm sorry I'm running out of space here, magnitude of r prime of 1, which is the square root of negative 1 squared plus 2e squared plus 0 squared. Please be careful here. This is the square root of 1 plus 4e to the 4th. Don't forget to square that coefficient. And now our unit tangent vector at 1, we're going to take r prime of 1 and divide by its magnitude. That is going to give us negative 1 over the square root of 1 plus 4e to the 4th, comma 2e squared over the square root of 1 plus 4e to the 4th, comma, I like the last one, 0. If you wanted to plug that into a calculator to find some approximate values, I think these are what I got. Negative 0.068, comma 0.998, comma 0. We're going to be doing that a lot this year. Get used to finding unit tangent vectors, folks. All right, moving right along. For the curve r, defined as root ti plus 2 minus tj, find r prime, then sketch the position vector of r1 and the tangent vector, r1. So we're going to do some sketching in 2 space here. So we have a 2-dimensional vector function. Let's start with r prime. So taking the derivatives component-wise, that is going to be 1 over 2 root t, comma, negative 1. Looks like it wants us to define r of 1, which would be 1 comma 1, and then it wants r prime of 1, it's asking about a tangent vector at r1, so r prime at 1. So this isn't the unit tangent vector, this is just the tangent vector, we get by plugging a number into our prime. That is going to be 1/2 -1. So if we wanted to graph a few points on our space curve, we could set up a table if you like. T, X, and Y, if we plugged in, let's see, 0, 1, and 2, just to get a few points here for our space curve. If I plug in 0 into the original r of t function, that would be 0, 2. Plugging in 1, we would get 1, 1, and then plugging in 2, we would get √2 and 0. Now, if I wanted to draw that, I think on my graph, I'm going to go up by 2 since I have a √2 there. Or, I mean, I'm going to use 2 lines for every 1 on the graph. So the point 0, 2 is right there. Then we have 1, 1 right there. √2 is a little less than 1.5, so I'll put that right there. So there is the beginning of our space curve r of t right there. Now, our position vector, r of 1, points at that point on the space curve. So in red, I'm drawing r of 1, our position vector. And then it wants the tangent vector, r prime of 1. So I'm going to start at that point where the position vector is pointing, and from there I'm going to draw a vector 1/2 -1. So think about that kind of like a slope. I'm going to go over a half, and then I'm going to go down 1. So it's going to be right there. And make sure your vector is pointing in the right direction. So when drawing that tangent vector, you got to be starting at that point that you're drawing the tangent vector at, and then we move just like we would, kind of drawing a line. Okay, moving right along. Example number 3. Find the parametric equations for the tangent line to the helix with parametric equations given by x equals 2 cosine t, y equals sine t, and z equals t. You'll remember, or you might remember from 13.1, we had an example of how we got this helix. So that sine and that cosine and 2 of the components, when we plug in t, that's going to give us a circular type motion. In this case, it's not an exact circle because the coefficients in front of the sine and cosine are different, so it's going to be an ellipse. And then we have a third component that is just defined as an increasing function t, so that's how we get our kind of circular motion, and as we go around in our circular motion, we go up. Now, maybe I should say elliptic motion, whatever. All right, we're going to find the tangent line. We're going to find the parametric equations of the tangent line at the point 0, 1 pi over 2. So what do we need for a line? We need a point, and we need a vector in the direction of the tangent line, which is going to be parallel to our tangent vector, r prime. So I think I'm going to first write our vector function component-wise here. So r of t is going to be 2 cosine t, comma, sine t, comma, t. And then, as a reminder, we need a point and vector parallel to the tangent vector r prime of t. So, probably makes sense to next find, I don't know why I just wrote 2 vector arrows, my bad, r prime of t, which is equal to -2 sine t, cosine t 1. We need our direction vector at the point that we are finding tangent to, so that's going to be, well, I guess we need to figure out what value of t sends us to the point 0, 1 pi over 2, huh? I think by inspection, you might all agree with me that that is when pi t equals pi over 2. So let's find r prime of pi over 2 to find the direction vector that's parallel to the tangent line. So that would be negative 2 sine of pi over 2, which is negative 2. Cosine of pi over 2 is 0. And then our last component is just 1. So there is our tangent vector at the point 0, 1, pi over 2. So we're going to use both of those to create the parametric equations of our tangent line at that point. That is going to be x equals negative 2t, y equals 1. We don't have it'd be plus 0t, but we don't need to write that. And then z equals pi over 2 plus 1t. So those are our parametric equations of that vector line right there, tangent to the curve at the point 0, 1, pi over 2. So what would the general tangent line equation for this helix for any value of t naught? Well, that point, t would equal t naught, and then our direction parallel at any point t naught would be, or we could think about it as another point going to t cosine, or 2 cosine t naught, sine of t naught, and t naught, which would give us generally x equals, I'm sorry, that is our point right there. I apologize. So 2 cosine of t naught plus t times, then plugging that into the derivative of r prime would give us negative sine of t naught. Y would equal sine of t naught plus t times cosine of t naught. And then z would equal t naught plus t times, and then the r prime component for z is just 1, so that'd be times 1. So that would give us a set of equations where we could choose any value of t naught, plug that in, and that gives you any line, anywhere else you want to draw a tangent line on that helix. Right. Sample number 4. So let's take a space curve r1 of t, which equals arctangent of t sine of t, t squared. Another vector function r2, which is t squared minus t, 2t minus 2 and ln of t. And we can see that they intersect at the origin. If you plug in 0, sorry about that. I brain fart right there. I apologize. We're not plugging in 0 for t. There are values of t that we can plug into all of them where they will be at the origin. Both of these two space curves contain the point 0, 0, 0. That does not mean t needs to be 0. Now, for this first one, what value of t will make all the components 0? That happens to be 0, because that will give us the point 0, 0, 0. So t equals 0 is when r1 is at the origin. That is not true for the other one, and that's why I just had to think for a moment. I was like, I can't plug in 0 into ln of t. That doesn't work. What value do you plug into ln of t to make that 0? That would be 1. So if you want to just double check for me, r2 of 1, that gives us 1 minus 1, which is 0, 2 minus 2, which is 0, and ln of 1, which is 0. So it's at the origin when t equals 1. So be careful with that. Don't have the brain fart like I did. We're not plugging in 0 in for t. They just both have a point at the origin. All right, find the degree measure of the acute angle between their tangent vectors. So we're going to go back and do a chapter 12 thing here, but we first need to find the tangent vectors. And how do we find tangent vectors? We need to find the derivative of both r1 and r2. So r1 prime is going to be equal to, got to remember some derivatives here, right? Derivative of arctangent of t, 1 over 1 plus t squared. Derivative of sine of t is cosine t. Derivative of t squared is 2t. Over here for the derivative of r2, so r2 prime is going to be 2t minus 1, 2, and 1 over t. Where are the slopes of these tangent lines? We need to plug in those values of t we figured out where we were at the origin. So for r1 prime, we're going to plug in 0, which gives us the direction vector, kind of like our slope, 1, 1, 0. While for r prime of 2, we're going to plug in 1, not 0. So that's the value of t where we're at the point 0, 0, 0. So that is 2 minus 1, which is 1, 2, comma 1. Now, thinking back, how have we found angles between two vectors? We are going to use a dot product idea here. So we're going to do r prime of 0 dotted with r prime of 2 of 1. That is going to equal to the magnitude of r prime 1 of 0 times the magnitude of r prime 2 of 1. Sorry, I wrote a 1 right there. Sorry about that. Times cosine theta. So we know that cosine of theta is equal to the dot product of those two vectors over the product of their magnitudes. All right, so we're doing the dot product between this red vector here, this blue vector right there. So that would be 1 times 1 plus 1 times 2 plus 0 times 1. In the bottom, the magnitudes. The magnitude of the red vector is square root of 1 squared plus 1 squared plus 0 squared, which is square root of 2, times magnitude of the blue vector, 1 squared plus 2 squared plus 1 squared. Square root of that is square root of 6. So that gives us 3 over root 12, which we could simplify. Believe it or not, this one actually simplifies nicely. 3 divided by root 3 is root 3, so that's root 3 over 2. Cosine of what angle is equal to root 3 over 2, the acute angle? So theta is going to equal 30 degrees. Pi over 6 if you want to do radian. But 30 degrees right there. Didn't even need a calculator. Look at us go. All right, some differentiation rules. As with all this stuff, it is nice to know these rules. You should look at them, you should think about them. First one's going to make a lot of sense. If you have two vector valued functions and you're taking a derivative of their sum, it is just going to be the sum of the derivatives. Similarly to our constant times a function rule from last year, if you have a constant times a vector function and take the derivative of that, it is just going to be that constant times the derivative of the vector function. We do have a product rule here. If you are paying attention to the notation, because we actually have 3 product rules, and you'll notice 3, 4, and 5, they're all product rules. What is 3? That's taking a function and multiplying it by a vector function. So for instance, number 3, you can think about it like doing x times the vector function, or maybe I should do t, not x, I'm sorry. T times sine of t, 2t cubed, and 7t over 5. I don't know. You can multiply a function into those components. So if you have a function times a vector, so I'm saying times, not product, times a vector, and you want the derivative of that, you have something that looks like the product rule, and you'll notice, pay attention to the boldings. We have f prime of t times the vector function u plus the function f of t times the derivative of the vector function u. We also happen to have product rules for dot and cross product. And you'll notice they look very similar. So if you are dotting two vectors and you want to take their derivative, it is u prime dot v plus u dot v prime. Similarly, for a cross product, if you take the derivative of a cross product, it is u prime cross v plus u cross v prime. Now, please take note, folks, of the cross product. Remember, the cross product is not commutative, so you have to be very careful that you do it in the right order. It is very easy to get that wrong if you're trying to use that rule by switching the directions of the cross products. It has to be in that way. So I'm going to tell you, always start thinking about product rule is the derivative of the first times the second plus the first times the derivative of the second. Be careful with the cross product one. Chain rule, very similar thing here. Notice that we have a vector function with a set of functions on the inside. You will see that we have a chain rule the same way, where we have the derivative of the outside, leaving the inside alone, times the derivative of the inside. And notice that this is just a function times a vector function, so that is multiplication. I wouldn't call that a product to confuse you with dot or cross product. That is just multiplying a function into a vector function. All right, so mentioned this right here. This is a big one. Star it, underline it, do something. Be careful with differentiating a cross product. All right, we are almost done here, folks. All right, additionally, if R is differentiable and the magnitude of R is constant for all t, then R prime is orthogonal to R of t for all t. In other words, if R of t times R prime t, or excuse me, R of t dotted with R prime of t is equal to 0. Right here, what this phrase is meaning is that this magnitude R of t is equal to some constant c. Visually, what is that saying? That if we have a constant magnitude of R of t, that means that we have a sphere. If the magnitude of t is equal in all directions that it can draw, it is, I said that wrong. Starting over. If the magnitude of R is constant, that means that where R of t points from our center, our origin, that curve lies on a sphere, because that curve is never more or never less. It is always exactly a radius, a certain amount of distance from 0, and no matter what the curve looks like. So you can see kind of a helix thing being drawn on the sphere right here. The curve could look however it wants, but if the magnitude is constant, that curve can be thought of as lying on a sphere, and R prime of t is always going to be orthogonal, meaning we'll always have a right angle between R of t and R prime of t because of the sphere. That is not necessarily the case for all other functions. All right, so we got some practice. You should try these on your own. I will write down some answers and talk through them, but you should be trying these on your own, not necessarily just watching me do them to see that you're using the rules correctly, okay, folks? All right, so if you're back and ready to check with me, I'm going to calculate the derivative of R1 dotted with R2 by differentiating the product directly. So the first thing I'm going to do is take the dot product. So I'm going to do R1 dotted with R2, which is going to be 2t, 3t squared, and t cubed, dotted with 0, 0, t to the 4th, which gives us 0 plus 0 plus t to the 7th, aka t to the 7th. And the derivative of t to the 7th with respect to t is just 7t to the 6th. Let's use property 4 now, noting that the derivative of the dot product can be calculated with R1 prime dotted with R2 plus R1 dotted with r2 prime. So r1 prime, we can go back up, look, and take our derivative of r1, which would be 2, 6t and 3t squared, dotted with 0, 0, t to the fourth, and we can add that to 2t, 3t squared, t cubed, dotted with the derivative of r2, which would be 0, 0, 4t cubed. Let's see, getting that dot products, those would be 0 plus 0 plus 3t to the, oh, you know what? I forgot something right here. That's 3t squared. That would have been bad. 0 plus 0 plus 3t to the sixth plus 0 plus 0 plus 4t to the sixth, which gives us 7t to the sixth. Would you look at that? The property works. All right, we got one more with the cross product. Got to be careful here. We're going to calculate the cross product first, then take the derivative, and then we'll find the derivative using product rule with the cross products. So let's do r1 cross r2. You got to be careful here because now we're using a bunch of t's and stuff. It's going to be a little messy here. So we have 2t, 3t squared, and t cubed, and 0, 0, t to the fourth. So this is going to give us 3t to the sixth minus 0. Get the opposite of 2t to the fifth minus 0. And then we're going to have 0 minus 0, which gives us the vector 3t to the sixth, negative 2t to the fifth, 0. Finding the derivative of that vector function right there gives us the vector 18t to the fifth, negative 10t to the fourth, 0. Now let's check to see that our product rule gives us the same thing. So this is going to be r1 prime cross r2 plus r1 cross r2 prime. So now I got to calculate two cross products. Maybe a little bit more difficult here, but here goes nothing. So r1 prime is 2, 6t, 3t squared. r2 is 0, 0, t to the fourth. We're going to add that to our cross product using r1, which is 2t, 3t squared, and t cubed, and then r2 prime, which is 0, 0, 4t cubed. All right, the first one gives us the vector 6t to the fifth. Sorry for this little hiccup. My pen just died, so I had to pause the recording. I'm back. So I was taking the cross product, so that would be 6t to the fifth minus 0. The opposite of 2t to the fourth minus 0. And then 0 minus 0, which gives us 6t to the fifth, negative t to the fourth, 0. Then we got to do another cross product over here, which is 12t to the 10th. I'm sorry, that's a 2. 12t to the 5th. And then we get the opposite of 8t to the 4th minus 0, and then 0 minus 0 right there. So we're adding that to the vector 12t to the 5th, negative 8t to the 4th, 0, which gives us our final answer of 18t to the 5th. If you look at that, it matches negative 10t to the 4th and 0. The properties work. All right, everyone. 13.2 WebAssign. Look at it over the weekend. Get that going. We got a quiz next week. Hopefully you have a wonderful weekend, and I'll see you on Monday.